Good morning, good afternoon, and good evening. My name is Fahmi. I'm gonna do a presentation about chapter 6, determinants and the inverse of matrix. The agenda is 6.1 determinant of matrix, 6.2 determinant of another matrix, 6.3 properties of determinant, and 6.4 LU factorization. 6.1 Determinant of a matrix. The determinant of a 2 by 2 matrix. You can only find a determinant of a square matrix. The determinant of a matrix A is normally denoted by that or determinant A, and is a scalar, not a matrix. The determinant of a general 2 by 2 matrix A is, like the example, defined as determinant A equals to A times D minus B times C. This is the example of 2 by 2 determinant. (6.1.3) Inverse of a matrix. This is the example of inverse of a matrix. Wronskian determinant. Wronskian determinant is used in differential equation to test whether solution to differential equation are linearly independent. If the Wronskian determinant is non-zero, then the solution are linearly independent. This is the Wronskian determinant. Determinant of another matrix. Minors and cofactor. Consider the general 2 by 3 matrix A as example. The determinant of the remaining matrix after deleting the row and column of an entry is called the minor of that entry. If we ask the minor of entry A, this one, so we eliminate the same row like B and C and D and G. So we take the E, F, H, I. Same as B, so we delete A and C, A and H. Then we take D with G, F with I. This is the example. Cofactor matrix. Let C be the new matrix consisting of the cofactor of the general matrix A. If A this matrix and C this matrix, where A is cofactor of entry A, B is cofactor of entry B, and C is cofactor of entry C. The matrix C is called the cofactor matrix and it is used in finding the inverse of A. Note that bold C represents the cofactor matrix and plain C is the cofactor of entry C. This is the example. Inverse of a matrix. Proposition 6.10. If a square matrix consists of two identical rows, then determinant A equals to 0. Proposition 6.11. Let A be an n by n matrix if CJK denotes the cofactor of the entry AJK for K equals to 1, 2, 3, and n. Then the form is like this. This is the example. 6.3 Properties of determinant. Revision of properties of determinant. Proposition 6.14. Let A be a square matrix, then determinant A transpose equals to determinant A. What does this mean? The determinant of a transpose matrix is equal to the determinant of initial matrix. Since determinant A transpose equals to determinant A, we can expand along a row or a column and achieve the same result. Proposition 6.15. Let B a matrix obtained from a matrix A by multiplying one row or column of A by non-zero scalar K. Then determinant B equals to K determinant A. Determinant properties of particular matrix. We can easily find determinant of particular matrix such as triangular matrix. What are triangular matrix? Definition 6.17. A triangular matrix is an n by n matrix where all entries to one side of the leading diagonal are 0. For example, the following are triangular matrices. For the A matrix is an example for an upper triangular matrix. For B, it's an example of lower triangular matrix. Another type of matrix is diagonal matrix. This is the leading diagonal. This is the example. Determinant properties of elementary matrix. What an elementary matrix is? An elementary matrix is a matrix obtained by a single row operation on the identity matrix. Example of 2 by 2 elementary matrix are. This is the example of 2 by 2 elementary matrix. This is the example. Determinant properties of other matrix. In the above, we restricted ourselves to elementary matrix. However, in this section, we deal with general matrix and find that they have identical result. Proposition 6.22. Let B a matrix obtained from the square matrix A by adding or subtracting a multiple of one row to another. We have determinant B equals to determinant A, interchanging row. This case determinant B equals to minus determinant A, multiplying a row by non-zero scalar k. In this case, determinant B equals to k determinant A. This is the example. The determinant of larger matrix. Proposition 6.19 stated that determinant of a triangular matrix is the product of the entries along the leading diagonal. This implies that if we can use row operation to convert a large matrix to a triangular or diagonal matrix, then evaluating its determinant is simply a case of finding the product of the entries along its leading diagonal. So this is the example. Further properties of matrix. Proposition 6.24. Let A be an elementary matrix. For any square matrix A, we have determinant EA equals to determinant EA. Determinant A, where EA is a valid operation. What does this proposition mean? It means that we can find determinant of each individual matrix E and A, and then multiply the scalars determinant E and determinant A to give determinant EA. And this is the summary. LU factorization. Introduction to LU factorization. L is a lower triangular matrix and U is upper triangular matrix. Solving a system of equation from Ax equals to B, where A is a 4 by 4 larger matrix, can be a tedious task. For example, to calculate the inverse of such matrix is a lengthy process. We are interested in finding the inverse of matrix A because we may want to solve Ax equal to B for various different B vectors. In this section, we establish a new numerical method to solve such linear system. This is the example. LU factorization procedure. Give a matrix A, can we form an upper triangular matrix U by using the following two row operation. The first one is multiplying a row by a non-zero constant. 2. Adding a multiple of one row to another. If the answer to this question is yes, then we can form an LU factorization of the matrix A. Suppose these row operations are represented by the elementary matrix E1, E2, E3, and EK. This is the example. Solving linear system. We want to solve linear system Ax equal to B and assume that we can break matrix A into LU. The linear system Ax equal to B becomes LUX equals to B implies LUX equals to B. Suppose applying the upper triangular matrix U to the vector X gives the vector Y, that is UX equals to Y. Substituting this into the above give LUX equals to B implies LY equals to B. This is the illustration in figure 6.15. This is we solve UX equals to Y and we solve LY equals to B. we need to solve ax equals to b. This is the example. That's it for my presentation. Thank you for listening. Bye bye.